then. Okay, I don't know what the quality of this is going to come out like, but oh, I don't think it shows up in the recording, if I recall. Oh, okay, good point. Good point. Here, let's get these guys. Yeah, there we go. Pull this off to the corner. That should be fine then.
Well done, David.
Mm-hmm.
I think I need to stand in front of the camera too.
Oh, yes.
Okay, hello everyone. First, thanks to everyone in the room, but thanks for tuning in if you're on Zoom. We have Jim Demel and one other person to thank for thinking of Zooming today. So let me say, in years past, we've had a few ICME graduates come and give a seminar. Students, former students who have gone to Apple and Cerebras and NVIDIA. But today we have a student who's hoping to graduate soon.
Yes, indeed.
So David, so this will be good practice for your defense, David.
Oh, yes.
David's been working on improving high performance computation in various fields, quantum chemistry, social choice theory, and what else? Certainly getting computational math going on real modern computers, right?
Oh, yes.
David, could you tell us who your advisors are?
Yes, I'm advised primarily by Alex Aiken over in the computer science department, and I'm also technically advised by Gianluca, since I needed an ICME co-advisor.
All right, okay. Oh, well, thanks for setting it up, David.
Oh, thank you for having us. All right, thank you very much. So, as Michael just warmly introduced, I'm David. I'm a student over in ICME, and I'd like to tell you a little bit about this work I've done on developing new algorithms and new proof techniques for high precision floating point arithmetic, which hopefully is a nice, very classical sort of ICME topic. So I'm sure this audience needs no introduction to the notion of a floating point number, but just in case, just to fix our notation, floating point numbers are a technique used to approximately represent real numbers with finite precision inside discrete information processing systems like digital computers. They're basically the same thing as scientific notation that you may have learned about in base 10, but they do this for base 2. So here I have a few examples of famous numbers written down both in base 10 scientific notation and as floating point numbers in base 2. And you can see they share a lot of common features. The main things you need to take note of are the fact that these numbers have a sign, right, plus or minus up front. They have an exponent, which is this little number telling you what the scale or magnitude of the number is. And then you also have what's called the fraction or mantissa or significand, which tells you what the actual value of that number is within these little buckets defined by the exponents. So you get the magnitude and the precision of these components. Now, your computer can work with floating point numbers in hardware. In particular, most of the computers that exist today can work with numbers stored in the IEEE binary 32 or binary 64 format. You may know them as single precision and double precision. And you've got these circuits that do addition, subtraction, multiplication, and division of these finite precision scientific notation numbers. These formats encode a certain pattern of packing the bits of the sign, exponent, and fraction into a 32-bit or 64-bit machine word. The details are not super important for this talk, but just know that there is this standardized format that everybody uses when they do applied mathematics and scientific computing. Now, what do we do when these formats aren't enough? What happens when we do these very precise calculations that need more than 23 or 52 bits of precision in the fraction to get a meaningful result out of them? Now, It's common advice given to programmers that you usually don't need to worry about this. Usually double precision is more than enough for all the applications that you're likely to work on. If that's, determining where a paragraph should be when you display a web page, or determining what color a pixel ought to be when you're rendering a video game. For those applications, even single precision is more than enough to get the fidelity you need. But in computational science and applied mathematics, we often run into problems where we run up against these precision limits. For one thing, there are some fields where you just need final answers to very high precision. Computational chemistry provides a great example, right? In computational chemistry, you have some molecule that you're trying to determine the conformation, the shape of. And nature really wants to minimize the free energy of this molecule, right? It's looking for the configuration that minimizes the potential energy of the resulting configuration. And you can see that there are sometimes these very close ties, right? These two molecules, their potential energy differs here in the 7th decimal place, which is much more than single precision can tell you, and accounting for some imprecision in your calculation, even double precision might struggle to give you this answer. But I want to make the point that actually, even in applications where you don't need the final answer to high precision, maybe you only need the final answer to 1 or 2 digits of precision, right? But even in those applications, it's often the case that even if you only need the final answer to moderate precision, you need to do the intermediate calculations to a very high internal precision in order to get out a meaningful result. And I can give you a simple example of a place where this occurs. Let's consider the problem of function optimization, right? Looking for the maximum or minimum of a given function. This is something that's secretly happening under the hood every time you do curve fitting or machine learning. Oh, it's a very common operation that, scientists, statisticians, mathematicians all have to do. Now, when you're looking at this nice infinite precision graph, you can easily see, okay, the optimum is right there at this point at the top of this peak. But you see, when you do this problem in finite precision, the computer is not working with this beautiful smooth curve that you see here. The computer is working with a rounded representation, right? It's working in finite precision. And you can see here the effect that now, once I've introduced rounding into the picture, that beautiful peak we had before flattens out into a mesa of optimal points, none of which can now be distinguished from each other using this rounded representation. Now, I've exaggerated the effect here on this slide to show you a nice pictorial view. In reality, these stair steps are much smaller, but the principle is the same. In fact, you can prove, I won't go through the proof here, but it's an easy application of Taylor's theorem, that if I'm only able to evaluate the function to a relative precision of epsilon, then I can only distinguish optimal values to a precision of square root of epsilon. And that square root cuts my effective precision in half. And so the upshot is that to locate the optimizer to precision p, you better be able to compute the objective function to precision at least 2p. And in fact, in practice, it's even more than 2p, because in practice, this function f is presumably going to consist of like the sum, difference, product, quotient of a lot of internal terms, right? And so there's going to be internal precision loss happening as well inside of the evaluation of f. So you need at least precision 2p in the final result, possibly more internally. And this isn't a problem that just affects optimization, right? I mean, this is one case where you need high internal precision to get out a lower output desired precision, but there are lots of problems that have this general sort of structure. If you're estimating derivatives by finite differences, for example, you'd better have f evaluated to a precision of at least 2p plus this factor here, what I'm calling the condition number of f, to account for internal precision loss. You better be able to evaluate the inside function to precision 2p to get a result as p bits. When you're calculating definite integrals, right? You have this condition factor coming from cancellation between the positive and negative parts of the integral. You better be able to resolve those differences finely enough to get the real answer out to p bits. And when you're solving linear systems or computing eigenvalues, there's the well-developed theory, the condition number of a matrix or the condition number of a particular eigenvalue given by how far apart its left and right eigenvectors are, telling you how precisely you should do the internal calculation if you want that answer. And even when it comes to just evaluating some transcendental functions, if you want to evaluate, the sine, cosine, the gamma function, the beta function, right? These internally need high precision in order to get out a result that's precise to p bits. Now, you can easily imagine, right, that when you're solving some complex scientific problem, right, Let's say you've got some data and you're going to do a function optimization to find the curve of best fit that goes through that data, right? Maybe then you're going to take those parameters you've estimated through function optimization, you're going to plug them in to some distribution like the gamma function or the beta function, right? Or the error function. And maybe you're going to take some numerical derivatives of that to estimate the Fisher information matrix. What have you? You can get into situations, right, where you're chaining together 3, 4, 5 of these operations, and you can easily wind up in a situation where even if I only need the final answer to 5, 10 bits of precision, I might need to carry out some internal calculations at the very core to like 100, 200, 300 bits of precision. So you see, this is a problem that potentially affects a wide variety of numerical computations. So what do we do about this, right? I mean, what happens when we surpass this barrier that machine precision puts for us? So you see, combining these inexact operations leads us to this problem. Well, one thing that we can do, and that numerical analysts have done for the last several decades, is to put our thinking caps on and try to reformulate the problem or reformulate the algorithm for greater numerical stability, to reduce the sensitivity to internal rounding errors so that they don't compound, right, in this constructively interfering way. And indeed, I mean, this is something you learn about in numerical analysis 101, right, in the shift from Gaussian elimination to QR factorization. But this sort of thing requires quite a lot of ingenuity, and it requires you to deeply understand the algorithm that you're working with to be able to identify the error sources, reformulate them in the right way. It has to be done separately for each type of problem that you'd like to solve. And finally, it's just not always possible. You do still run into cases, even if you have all these tricks in your tool bag, you still run into these tricky problems that are difficult to reformulate in a numerically stable way, where no matter how you rejiggle the equations around, you still just run up against a fundamentally hard computation. So another thing that you can try to do is go to arbitrary precision arithmetic libraries. The problem of doing arithmetic with more bits of precision is well studied and well covered by some popular open source software, like the GNU multi-precision library, NPFR, which is a variant that does correct rounding, more recent ARB and Flint libraries for computational number theory, and CLN is another entry in this space. And these libraries will let you do arithmetic at any user-specified precision level, right? Using software to simulate an extremely wide floating point unit. These are very good libraries. They're mature and well-tested, and they have proven accuracy. In fact, for MPFR in particular, I mean, the authors of MPFR wrote a lot of proofs of novel algorithms for computing transcendental functions. A lot of serious work went into these things. But these libraries only run on the CPU, and they can be thousands of times slower than native machine arithmetic, even if you're only working at machine arithmetic levels, right? Even if you're only asking GMP to do 128-bit calculations, it's still going to use algorithms that are thousands of times slower, and they need to be. And we can understand why this happens if we take a look inside under the hood at what these libraries are doing. So here is the floating point addition function taken out of the latest version of GMP, the time that I made these slides. And there are a few features that should immediately stick out to you if you're a programmer. The first thing is there's dynamic memory allocation, right? The result may potentially need a huge number of bits, might not fit on the stack. So you better do a malloc call right in there. And then you can see what happens next is a bunch of branching case analysis, right? We have to consider all these possible cases of how the two addends U and V could overlap with each other and execute different operations in each case. That sort of branching can be quite expensive, especially if you're working on a data parallel processor like a GPU, right? For CPUs, this might be okay, but even there, branch misprediction can cause quite a large computational cost. So these programming constructs just fundamentally aren't very suited to the kind of high-performance scientific computation that you might hope to do in parallel fashion today. Now, looking at this, you might think this is ridiculous, right? I mean, come on. Imagine walking the free list every single time you want to add two numbers. Of course, this is going to lead to a huge slowdown in your program. But the point of this slide isn't just to dunk on the authors of GMP and MPFR, right? I'm not trying to say that these are poorly designed libraries. Like I said earlier, these are excellent libraries designed with asymptotic efficiency in mind for massive numbers that could have thousands to millions of digits. They do clever things like FFT-based multiplication, right? To avoid the n-squared cost of naive multiplication. And in this regime, when you're working with these massive numbers, right, these complex control structures and memory allocation are perfectly reasonable. But we often find ourselves in scientific computing in the opposite situation, where we only need a small increase in precision to 128 or 256 bits without going all the way to huge numbers with millions of bits, right? So what do we do in this case? Well, when you think about what it is that makes these libraries slow, right? What you can see is that, floating point at its core is defined in terms of this complex branching case analysis, right? The actual representation under the hood requires you to consider all these different cases using the text right out of the standard. And the only reason that your native floating point hardware is fast is because it can do all this branching in hardware, right? In circuits. And circuits are always going to beat software for a problem like this. So even if we were to take out, say, the memory allocation, right, put everything on the stack, allocate everything statically, these control structures will still remain. But you can get some inspiration from this point, right? You can look at this and say, hang on, I have circuitry in my computer that can do all this complex branching case analysis for me. Can't I just use that somehow to do my higher precision operations? And indeed, it turns out you can. There is a very clever way of doing this. Called, I think in general, a floating point expansion. And the idea of floating point expansion is to represent high precision numbers using a sequence of successive machine precision approximations. The idea is, say, for example, suppose you've got a machine that can store 6-digit numbers. I'll do this example in base 10, but the principle is exactly the same in base 2. I can store this high precision number using a pair of machine precision numbers, one of which stores the upper half and one of which stores the lower half. In general, what I could do is if I have some high precision constant C, I want to machine numbers, I would find the closest representable machine number, what I'm calling RNE here for round to nearest. I find the closest representable, take that as my first term, then I would, in exact arithmetic, subtract off whatever value that was, and I'd find the closest machine number to the residual, whatever's left over after I take out that top bit. And then I do the same thing. I take out that value, look at what's left over, put that into another machine number, and I keep doing this for, as in principle, as long as I wanted to, bounded only by the underflow limit of your machine. So I can get whatever precision I wanted that fits within the exponent bounds of my floating point format. But doing this is a delicate matter. It's not so easy, and it brings up a few issues of how to design the algorithms. Right? The very first one is this idea that a floating point expansion has to be non-overlapping. So in order to get the maximum precision, when I split a number into multiple machine words, I better make sure that the subsequent machine words are sort of as far to the right as possible, right? That the first machine word really is the closest possible approximation so that I'm not redundantly representing bits shared between the mantissa of these two words. So here's an example where I have the first two words overlapping in their last two bits, and I don't get the full precision. If I've clear that overlap out, you can see I can get two extra bits of precision in this case. We're not representing these two ghost digits anymore. And in fact, the best you can do is actually to have a spare bit in the middle. If you round this number to the closest representable, which in this case causes you to round up. Rounding up means you take the ones complement of all the digits that come afterwards. And so in this case, you get one extra zero. You can get that one extra bit, one little bit of daylight in the middle there. And so it's very important that when we work with these expansions, we're going to have to maintain this non-overlapping property. So how do we do that? I mean, if I want to add or multiply or subtract or divide two of these floating point expansions, what do I do? You might think it to be impossible, actually. It seems like there's something fundamentally missing here. And to point out what exactly it is, let me make an analogy to integers, right? With integers, it's very easy from two 64-bit adders to construct a 128-bit adder. All you need is the carry bit in the middle, right? You add the low words, just like you did in elementary school. You add the digits one by one. You hit the point where you carry, and then you bring that one digit over. And in fact, this is such a common operation that it's supported in hardware on a lot of common processors. They always have an ADC instruction that does add with carry. But floating point arithmetic is fundamentally different. It rounds instead of carrying, and it destroys the bits that were rounded off. So again, to illustrate here in base 10, suppose we're working in 3-digit arithmetic here, right? If I add these two 3-digit numbers, I get out a 4-digit number, and that 4th digit becomes the carry bit, which I can then access when I add up the next digits down the road. But if I do this in the floating point domain, what happens is I add up these numbers, I get the three most significant digits out the other end, and then this rounding error, 0.24, is rounded off. If that happens, how could I possibly work with floating point expansions, right? After I add, say, the first word to this one and the first word to this one, I have some rounding error that I need to propagate into the subsequent machine words, or else the whole thing is going to be nonsense, right? The whole result is going to be wrong past that point. But thankfully, there is a way to do this. There is an ingenious algorithm called two-sum, due, I believe, to Ole Moeller and Don Knuth in the mid-late 60s, that allows us to get around this fundamental limitation. What two-sum does is it takes two numbers, called A and B, and it spits out two numbers called S and E. And what those two numbers are, well, S is the rounded floating point sum of A and B, right? Which I symbolize using this rounded addition operator because it's rounded. See, cute little pun. I can't take credit. That one goes back to Knuth, actually. But what two-sum does is it computes the rounded sum, and then it computes the exact round-off error, the difference between the true mathematical sum and the rounded sum. It recovers this bit that was rounded off. And miraculously, it does this using only rounded floating point operations. So if I have access to only a 64-bit floating point adder, I can do this procedure to extend out the precision, provided that that adder correctly rounds this result to nearest. Any time-breaking rule is fine, but there is one little nit down there. So how does this actually work? Oh, a screenshot of the history, and in fact, the exact page in Art of Computer Programming where this algorithm was written down by Knuth. So how does this actually work? What it does is it first computes the floating point sum, as you'd expect, and then it computes what I like to call the effective value of A. You take the sum you computed and you subtract off B, obtaining a rounded result. This number is not going to exactly represent A, but it's going to represent the contribution of A to the sum, its effective value through this rounded lens. You can do the same thing for B. One little thing is you use the effective value for A in computing this difference. So you have to execute this before this. And now what you can prove is that at this point, the effective values of A and B exactly sum up to S. Now you look at the differences between A and B and their effective values. And I call those the rounding error coming from A and the rounding error coming from B. And then it turns out if you add those two numbers up, you exactly recover the rounding error of the sum. And then you just return those two values. To give you some intuition, let me walk through this with actual numbers. Again, I'll use an example in base 10, but the principle in base 2 is just the same. So using those two numbers from before, 93.7, 7.54, let's add them up. And remember, we're doing rounded arithmetic, so we're going to round this result off to 3 decimal places. We're going to get 101. Now, I'm going to calculate the difference between 101 and 7.54. That'll give me a number that, again, doesn't fit in 3 digits, so I'm going to round it off, and I get 93.5. So 93.5 is the effective contribution of A to this sum. Now, I look at the difference between my rounded sum and the effective value of A. I get the effective value of B. It's 7.5. And you can see 93.5, a little bit different than this, and 7.5, a little bit different than this. But once I take those two differences and I add them up, I get exactly that 0.24 that went missing in this original rounding. What a miracle. We've recovered that rounding error. And so I can return these two results, both of which individually fit within 3 digits. And you can see that's how two-sum works. Now, it takes a whole lot of pencil and paper proving to check that two-sum does indeed work in this way, no matter what the relative ordering of A and B are, right? What their magnitudes are, how their mantissa may overlap, if A is over here and B is over here, or if they partially overlap, or if they completely overlap. It's a long and detailed argument that requires several pages of case analysis inside Art of Computer Programming. But you can check it out in every case, assuming correct rounding, this whole procedure works. And so two-sum gives us the fundamental keystone we need to do arithmetic with floating point expansions and to extend arithmetic past machine precision. But even still, having this tool in hand, we still have a big problem. Here's this. Two-sum now allows us to exactly add 2 floating point numbers to each other. But if we're going to do arithmetic with expansions, we need to accumulate more. For example, if I just say, okay, I want to do 128-bit arithmetic, all right? I want to use two machine words to represent each of my numbers. Then to add those two expansions, what I need to do is take x0, x1, y0, y1, these two expansions we can assume to be non-overlapping, and then produce a non-overlapping two-term expansion of their exact sum of all these four numbers. How do we accumulate these four inputs into the exact sum in two outputs? And this is a problem with quite an interesting history. This technique was first proposed, I believe, by Decker in 71 under the name double-double arithmetic. And it's an interesting history that I'll go a little bit into here. So in his original paper, Decker proposed this algorithm, which he called add2, to calculate the double length sum of two of these expansions in this way. He writes x and xn instead of x0 and x1, but same difference. And his algorithm is given here in, I think, some sort of ALGOL syntax. Now, he uses a branch in this algorithm, but mathematically, that branch is equivalent to this algorithm written in terms of two sums. So you can see what's going on here. So you take, oh, I apologize. There seems to be a typographical error here. These should be x0 and y0. You take the two high words, you sum them up, then you compute these sums of the intermediate terms, and then finally you two-sum these two results. It's not so easy to understand what this algorithm is doing when written down in this representation. It's a bit tricky to see. So let me instead introduce a graphical notation for these kinds of algorithms, inspired loosely by sorting networks, if you happen to know what those are. What I'm going to do is I'm going to write down the two-sum operation as this double plus, and I'm going to write down just plain old floating point addition as just being a two-sum, except you discard the error term, right? You just get rid of it, you don't care about it. And then what I'll do is I'll write down this network representation of the algorithm. Here in this picture, the inputs are here on the left side, and they flow through the diagram left to right. And whenever they encounter one of these two-sum gates, this operation gets executed on them. So Decker's add2 algorithm looks like this. It's a very intuitively appealing, little staircase that accumulates all these numbers up into two terms. And written down this way, you think, oh, this looks like a very reasonable algorithm. In fact, if you were to interpret this as a sorting network, this would be a perfectly valid network for partially sorting four inputs into two outputs, assuming that this is greater than this and this is greater than this. But floating point accumulation is a much more difficult problem than sorting. It has many more failure modes. And in fact, this algorithm, no shade to Decker, but it can be totally incorrect. In fact, there are inputs you can give this algorithm such that the computed sum has relative error more than 100%. It means that the first bit of the answer can be wrong. And the reason that sort of thing can happen is because supposing that x0 and y0 nearly cancel out, right? If they're nearly negatives of each other, you can wind up in a situation where this term down here contributes significantly to the sum, but is discarded too early in this analysis, leading to a great big relative error, depending on the relative magnitudes of these two numbers. So this was realized some time ago when I think some members of the audience, David Bailey, Jim Demmel, Sherry Lee, were working on the XBLOS library for extended precision linear algebra. They saw this error and they proposed a new algorithm for adding up two double doubles, which they called the DD-add in their paper. And it's written down in code here, but again, it's hard to understand in this notation. So let me move over to that graphical notation again. You can see DD-add does the exact same prefix of operations that Decker's add2 operation did, but it includes one extra little cleanup step at the end here, where we two-sum these two error terms, and we accumulate that result back into the final answer before returning it. And this does indeed fix the issue, the failure mode that add2 exhibited. But the correctness of this algorithm is a very interesting story with a couple of twists and turns. So in the original XBLOS paper, the authors claimed this addition algorithm had relative error bounded by 2 times 2 to the minus 106. Recall here that an IEEE double has 53 bits of precision, right? So this is essentially saying that, both machine words fully contribute to the precision, except the last bit can be off. That's a pretty reasonable error bound. It's what you would want this algorithm to exhibit. But unfortunately, it's not quite true. The analysis missed this case where two of the error terms can interfere constructively, giving a counterexample with relative error 2.25 times 2 to the minus 106. Now, this is not a grave mistake. Okay? This does not in any way invalidate the usefulness of XPLOS. But this goes to show you that even people who are floating point experts, right? I mean, real luminaries of the field can get this kind of analysis subtly wrong. And these guys found a counterexample with error 2.25 and conjectured that this was in fact the upper bound, that this was the worst you could do. In fact, that claim is also wrong. I found an even better counterexample, and in fact, it turns out I was not the first to find this. Some other folks found this too, where the discarded terms have relative error 3 times 2 to the minus 106. So you can get a little bit worse than that as well. Now, this is in line with the bound that this team in the middle proved here, but it just goes to show how subtle this analysis is and how the literature on this subject is sort of punctuated with refutations and corrections and then further corrections to those corrections.
Excuse me.
Yes.
Would these things be easier if you use truncated arithmetic? Rounding is often trickier than truncated.
That's a good question. I'm not sure it would be. I know that there is a variant of the two-sum algorithm that works with truncated arithmetic instead of rounding. It requires more operations, but how to carry the analysis through past that point is not entirely clear to me. But I think you'll see that the technique that I propose to analyze these algorithms would probably carry over to truncated arithmetic, changing some of the details of the analysis, rounding cases. So at this point, I want to pause a little bit and talk about the proof that this team from, I believe they're a French team, these Jolds authors, talk about the proof that these folks gave of the relative error bound for DDAD. Because this is a very difficult and detailed proof, right? I mean, you can see here that they have to consider all of these different cases, depending on whether the high words overlap in a certain way, whether the low words overlap in a certain way. They have to consider all these different possible patterns of inputs and outputs, and they have to do this complicated analysis within each case. And I mean, it gets even worse. We're not even at case 2 yet, right? This goes on for pages and pages. And it's no wonder that when you have a proof of this complexity, it's very easy for a minus sign to get accidentally transposed somewhere into a plus, right? Or for a term to get accidentally dropped. Doing this analysis by hand, I think, is, sure to lead to problems of this kind. But this got me thinking, right? It got me thinking because the overall structure of this proof is to consider this huge number of cases, right? To do this combinatorial explosion, and then within each case, to do relatively simple mathematics. And you can see, these are just linear inequalities, right, in the floating point variables. And even though doing the case split is, tedious and requires lots of detailed work, the actual analysis is not that hard. And this is the kind of argument that is really suitable for computer automation. So I started thinking about how to do that, how to get these error bounds into a rigorously provable state using automatic reasoning tools. So first, we need to think about what we actually need to do, right? To prove the correctness of one of these algorithms, a class that I'm calling floating point accumulation networks, in analogy to sorting networks, well, you need two things. You need an error bound on the discarded terms, right? You need to see that everything you discard is at most 2 to the minus 106 or whatever times the leading term you eventually return. And you also need to show non-overlapping invariance on the terms that you keep, right? You need to show that they're properly separated so that you are getting your 106 bits of machine precision. So what it means is we just need to rule out all possible invalid outputs, assuming that we have valid inputs. Now, viewed in these terms, you could in principle prove one of these claims using a SAT solver, right? You could write down the great big Boolean formula that represents floating point addition or subtraction, right? Write down the whole two-sum algorithm at a gate level representation, convert that whole thing into a great big Boolean formula and ask, is this satisfiable? And that would work. You would get an answer that way. The trouble is just for 64 bits, you wouldn't get an answer before the sun explodes. We all cease to exist. I mean, you would be, solving an NP-hard problem on an input that's, just millions, possibly billions of terms long. So that approach is not going to directly work, but it can be tweaked into something that is viable. You see, the problem with that approach is that you explode into this huge number of binary variables representing the intermediate values of every single bit in the computation, right? You're writing down this bit-precise formula. You've got to propagate all the way through it. You'll never get through all those cases by brute force. But the bounds that we're interested in don't involve all of the bits of the number that we're looking at, right? They basically just involve bounds on the exponents and possibly some, leading, trailing zeros of the mantissa we need to worry about. So what I propose to do is something that I call the sign, exponent, leading, trailing, zeros, ones, or the SELTZO abstraction, abbreviated that way. So instead of the whole floating point number x and its full bitwise representation, let me consider just its sign and exponent and the number of leading and trailing zeros in the mantissa of x. Like I said, these variables are enough to prove the bounds we're interested in, right? They allow us to state these correctness properties of non-overlapping and error bounds on discarded terms. And moreover, the two-sum operation is very well behaved under this SELTZO abstraction. If I know the signs and exponents of the inputs, I can predict the signs and exponents of the outputs to a pretty good degree. I can't tell them to you exactly, of course, because there are many possible inputs within each SELTZO bucket, but I can put bounds on the possible output buckets in this abstraction that they lie in. And so, with the assistance of an automated theorem prover, I went around proving a bunch of lemmas about possible inputs and outputs of the two-sum operation through the lens of these variables. And what this has produced is a sort of semi-automated list of a few hundred lemmas, each of which look at a very particular case, inputs that fit this particular pattern, and tell you what the possible outputs are. I can also prove to you that these are the tightest possible lemmas, which is to say that every abstract output that is not explicitly forbidden by these lemmas is actually realized, is actually witnessed by some concrete inputs. So now, okay, I still have a pretty complicated abstraction here, right? I still have a pretty big mess of formulas, but it's a much smaller mess than just the Boolean explosion would give you. And importantly, it's one that's tractable for linear programming solvers. So this new technique for proving error bounds on floating point accumulation networks consists of setting up an integer satisfiability problem rather than a Boolean satisfiability problem, which is basically the same thing as an integer linear program. It's just got ands and ors in there in addition to the other allowed operations. So what you do to use this new technique is you take your floating point algorithm, right, and you set up SELTZO variables, this little six-tuple here, for each of the terms under consideration. Then you construct the actual statement that you want to prove satisfiable or not as a logical conjunction of three kinds of constraints. The first things you need are what I call consistency constraints that just ensure that these things are valid values that are witnessed by a natural floating point number. Things like if you're working in double precision with p equals 53 bits, well, these numbers better sum to less than 53. And the exponent's got to be bounded, and the sign can only be 0 or 1, things like that. Then I put execution constraints on the inputs and outputs of each of the two-sum gates in my network. That's that big family of lemmas I showed you before. It's a big system of hundreds of linear inequalities. And then finally, I put on counterexample constraints to describe the negation of the property we want. So I say, okay, I want to take a look at outputs that are not that are overlapping or that violate an error bound. All right. And once I've set up that whole thing, I can plug it into what's called an SMT solver. It's like a SAT solver, but allows for other variables in other domains than just true and false. And if the SMT solver tells me that these constraints are unsatisfiable, then I know that no counterexample exists. Because if a counterexample existed, it would give rise to an abstract counterexample, which would then be a satisfiable solution of this problem. Now, of course, there's one wrinkle. When you pass to this sort of over-approximation of the true behavior, you get a procedure that is sound but not complete. If these constraints turn out to be satisfiable, then a counterexample might exist, but there may be gaps between the abstraction and reality. In that case, the answer is indeterminate. But, as I'll show you later, this technique is precise enough to prove best possible error bounds on a lot of these floating point algorithms. And here's just a picture of those consistency constraints that I mentioned on the previous slide. Of course, you can see details of all this in a paper, in a manuscript that's currently under review that I'm happy to send to anybody in the audience. So using this technique, I went off and found a better, more accurate double-double addition algorithm. The network representation looks like this. And as you can see, compared to DDAD, the previous algorithm for double-double addition, it's got a few structural differences. It starts out with this same pair of floating point accumulations up at the top, but then instead of following Decker's add two pattern, it instead reaches across and does another round of parallel two sums staggered in this way. And then it cleans up the result using that staircase pattern from before. This was discovered by a computer search. I basically just tried out a bunch of examples, constructed these CELSO abstractions for all of them, and saw what error bounds I could get out. And in fact, you can prove using that technique that this new algorithm has a tighter relative error bound. Oh, my apologies. There's a horrible typo on this slide. That should be a 3. You can prove that this algorithm actually does have a tighter error bound. It gets one more bit correct than DDAD did. Again, not a huge difference. But the simple fact is that everyone who looked at double-double addition before seems to have missed this alternative algorithm. And more importantly than getting one more bit right, it also has lower depth, right? If you've got a superscalar processor, you can execute these two sums in parallel. So this whole thing has got depth 4 as opposed to depth 5. So this whole thing allows you to do double-double arithmetic a little bit faster than DDAD did. And speaking of faster, I just want to show you that doing verification using this CELSO abstraction is indeed quite a bit faster. I mean, so what I've done here is I've compared verifying this error bound using the CELSO technique I've just described to using a few of the leading SAT and SMT solvers on the direct bitwise floating point representation. And you can see here that when you work with these smaller formats like 16 and 32-bit, some of these solvers can just barely do it, right? I mean, it takes hours to days, and all these DNFs represent more than 3 days of continuous execution. But you can sort of extrapolate out, that once you get to 64, 128, this would take weeks. But our technique, solving this reduced integer satisfiability problem, takes it down to a fraction of a second. And importantly, the difficulty of this problem doesn't increase as the precision increases, right? Because the precision p just appears as another variable inside these inequalities, it doesn't actually make the problem any bigger to increase the precision. So you can manage to get very fast verification. And you can also see, oh no, not a minute. I'm missing a slide. Oh, yes.
What's the difference between observability here and
Oh, yes. Good question. Sorry, I didn't explain this. So some of these automated theorem provers will actually reject a problem as being unsolvable using the techniques that theorem prover implements. In particular, Colibri is a theorem prover specifically for floating point algorithms. And the way it works is instead of this CELSO abstraction, it uses interval enclosures. So it's basically proving interval bounds on all of the variables inside a floating point algorithm. Now, the problem with interval analysis, right, is that it is completely inapplicable to algorithms like two-sum that are doing sort of precise reasoning about the error, about rounding errors inside of inside these precise, what are called error-free transformations, right? Interval bounds will just completely enclose all the possible values and give you no useful information on what the error values actually are. So using that technique, you can't get anywhere analyzing circuits like this. You really need to do some kind of bitwise reasoning about the actual values of the mantissa propagating through the network. And what we show is that you don't need to reason about all the bits, just reasoning about these is sufficient. Now, there's supposed to be a second table back here. I apologize. It seems to have fallen off the slideshow, but luckily I do have the paper handy and I can just show it to you in the manuscript. A second table that shows you how precise our analysis technique is. So one natural question you might be wondering at this point is, okay, I propose an abstraction that uses these 6 variables, sine, exponent, and then leading and trailing zeros and ones in the mantissa. Did you really need to consider all 6 of those variables? You might be able to get these proofs by considering only the sine and exponent, say, or maybe only the sine and exponent and just trailing zeros, since that's all you need to get these non-overlapping properties that you want. And so we did that study. I constructed a reduced set of these lemmas, eliminating the variables for leading ones, leading zeros, and trailing ones out of them, and set up the corresponding satisfiability problems. And what you can see is that these actually do prove non-trivial bounds, right? This technique will get you a bound of 2p minus 7 instead of 2p minus 2 or 2p minus 1. So it actually is a very interesting model to consider, but it is not the best possible, right? You really need explicit modeling of those mantissa bits in order to get the tightest possible result. And it's sort of understandable morally why this is the case. Because if you look at the counterexamples that have been found to these other algorithms, right? The counterexamples that people tend to find, like these formulas here, they're always numbers that are either at or very near powers of 2, right? Because powers of 2 delineate the bounds from one value of the exponent to the next. These are the places where floating point accumulation networks sort of screw up the most. And so the Celso technique is really nice because it gets more and more precise the closer you are to one of these powers of 2, right? Powers of 2 and the numbers near them are precisely the floating point numbers with a lot of leading zeros or leading ones in their mantissa. So these inequalities that I have become tighter and tighter as you approach these pathological values, while they're loose in a way that doesn't harm the analysis for the sort of vast majority, right, the sea of other floating point numbers that are away from these special values.
Can you go back to the other table you just showed?
Yes, absolutely.
What's the difference in the arithmetic speed on the less accurate approximations? Are you doing fewer operations to get there?
What do you mean in terms of the
Computational speed. If I didn't need 2-bit, 1-bit error, if I could get away with 6-bit error, would I run faster if I did that?
That's an excellent question. So this particular table is just about what bounds you can prove for a fixed algorithm. The algorithm itself doesn't change with the analysis technique. But it is a great question to ask that if you only needed, 2p minus 6 precision, could you get away with a simpler network than what we found? Oh gosh, I know there's a figure for it somewhere. There we are. Could you get away with a simpler network than these two? I have done a little bit of analysis into this problem, and I think the answer is no. I think you need at least 6 two-sum gates in order to have sort of a non-catastrophic algorithm that doesn't have a failure mode like Decker's original add 2 did. We're going to have the whole answer corrupted by rounding error.
In the algorithms I did for the Itanium, I added x0, y0 instead of x0, x1.
Oh.
Y1, yeah, x0, x1. Got the right, to reduce the rounding, but I was truncated.
Interesting.
And so I wonder if you truncate, if you would have a different graph.
Yeah. So to analyze the case of truncated, I mean, I would have to basically rewrite all the lemmas that involve the parity case, right, of rounding to nearest even. But I think that is possible. I mean, I think we could concoct that set of lemmas and then reanalyze each of these networks in that case to see if you happen to get, one better.
I did it on the intuition that I'm adding numbers that are closer in magnitude, so fewer.
Yeah.
Yeah.
Gotcha.
The intuition.
Fair enough. Okay. Well, that just about wraps up the presentation, since I guess my last slide just disappeared on me there. So thank you all very much for listening. Sorry for this sort of anticlimactic ending, but I'll be happy to take any questions from the audience at this time.
One little oddball one, if you can hear the peanut gallery. At one point, you mentioned that you were producing the best possible, I believe, networks. Does that also mean that you can produce counterexamples for anything else?
Ah, yes, a great question. So this analysis technique, it turns out, does produce, well, okay, let me step back here. So when you're analyzing using these abstract variables, right, and what I call the cells of abstraction, the counterexamples that you get out of a satisfiability solver are not full floating point numbers, right? They're just tuples of sign, exponent, leading, trailing zeros and ones. Now, in all the cases I've looked at by hand, those abstract counterexamples are witnessed by an actual concrete counterexample. You can fill in the rest of the bits of the floating point number in such a way as to realize that abstract counterexample when you use the sort of full powered model without taking away any of the variables. But I don't know if I can prove that to be true for just an arbitrary floating point accumulation network. So the analysis technique is tight in all the cases I've looked at so far, but I do not know how you'd go about showing that in general. I think that's okay though, because what you'd want to use this technique to do is find new algorithms for specific operations like double-double addition or triple-double or quad-double addition. And once you have that particular algorithm found and set in stone, only that particular guy needs an error analysis anyhow.
Thank you. Great answer.
Thank you.
Have you looked at multiplication?
Great question. Not yet, but I plan to. So multiplication also requires this sort of accumulation step using two sums at the very end after you've computed your, mn terms, expanding out applying the distributive property. It produces, input values that are not completely generic, right? Assuming that the inputs are non-overlapping, the outputs should all have sort of known patterns of, how far out in terms of the exponent they are. And it should be possible to use this technique to find better double-double multiplication algorithms as well. That's what I plan to do next, but not there quite yet.
That's where the algorithm simplified if you have access to the hardware sticky bit.
I see. Gotcha. I'll have to write angry letters to Intel and AMD, telling them to give me an instruction to get that value.
It's there and they just won't let you see it.
Yeah, oh my goodness.
Oi, I'm at AMD.
Oh, excellent. In Zen 6 or whatever, please give us the sticky bit.
I know, working on it.
No, thank you. We appreciate the work that you do. Now, actually, the work that was done to find these networks, I actually carried out on a Zen 5 processor, using the new AVX 512 implementation, which is really nice. This is an aspect of the work that I didn't talk about during the talk, but the process of finding these things is very akin to the process of finding sorting networks, right? Where you're doing this sort of evolution of, candidate algorithms, testing them all against a bunch of random inputs. And then if they survive that battery of tests, okay, then you go and you try to construct a formal proof. And having those really wide vector units to push like 8 tests at a time through one of these networks is really helpful. Right. Any other questions from the Zoom audience or? Oh, yes?
I have a question, David. An early slide, you mentioned that functions like sine and log, to get p digits, you need two p somewhere. So, for example, a double precision sine, does the hardware really have quad precision inside it?
So it depends on the implementation. As I understand, you can get away with doing the internal calculations in something that doesn't exceed double precision very much, if you're willing to accept a few ulps of error in the results. But if you want a correctly rounded result, then you really do need the very high internal precision to make sure that you get the last mantissa bit right when you round back to machine precision.
Well, what do the Intel chips have? Do
Ah.
they have P or 2P?
An interesting question. So it turns out actually that people don't really use the hardware sine and cosine instructions anymore. They're present in the x87 floating point unit, but these days everyone prefers to do them in software because software is actually faster, it turns out, than the 387 implementation.
Software is pipelining. I
Yes.
think it's slower for individual one, but it's pipelining. Same thing for division.
Ah, I see. Yeah.
So tables are now very expensive. Lookup tables are now very, very expensive in hardware. So that's kind of where it went. It wasn't that way.
Oh, I see. I see. Interesting. So I guess there were just sort of, big tables that are being looked up inside the FPU. But yeah, so if you look at the software implementations that exist, particularly the correctly rounded libm implementations that exist now, they're all doing double-double or triple-double internally.
They really do need 2P or 3P in software.
Mhm.
Oh.
There's a theorem from Belkahan. You need 2P plus 1. And Peter Markstein found a very nice trick to avoid the plus 1. And we were able to show in our multi-precision division that there's exactly one number that needs the plus 1. 1 over 1 plus up. Everything else only needs 2P.
That's one exception among all flow.
But the point what that means is that you only have to do double-double in hardware. You don't have to do triple-double.
Mhm.
That's a big one.
Oh, yes. Save a lot of transistors with that one. All right. Any other questions before we close out the hour here?
Sounds like we need another David Jang to study not the rounding arithmetic, but the truncated. That's right.
Oh, yes. No, I mean, well, the procedure for discovering these lemmas is semi-automated. I could run it for truncating arithmetic, assuming, of course, I have access to a processor that executes, underlying.
The floating point standard calls for rounding modes.
Yes, indeed it does.
So you need to write a little assembly language program that you can set the rounding mode.
Yes. Yeah, indeed. If you got a IEEE something more compliant, which I actually don't know. See, the thing is, I did these experiments in 16-bit floating point, right? Because I can actually enumerate all 2 to the 32 pairs of 16-bit numbers and feed them all through a two-sum. I know that the single and doubles are fully IEEE compliant, but I'm not sure if for float 16 they may be only implemented round to nearest. I'll have to look.
Operations on binary 16 are not defined in 754. The format is defined, operations are not defined.
That's true. It's only a storage format or an interchange format, I think is the language
Yes.
standard, right?
Yes.
Indeed.
Oh, one final quick one.
Oh, yes.
You mentioned solving an integer program.
Mm-hmm.
What size are you talking about?
So the size is proportional to the size of the algorithm that you would like to analyze. But for these floating point networks that we're looking at here, oh, there we are. You get something like a couple hundred inequalities for each two-sum gate that's present, plus a fixed number of a few dozen for each variable.
Well,
That's in there. Now, the tricky thing is,
pretty big.
it is indeed. But what makes these things feasible is, well, okay, there's a few things to describe here. One, these aren't just integer programs, in the sense of, ax less than or equal to c, x greater than or equal to 0. They're what's called, I guess I should call them satisfiability problems, in that they have logical conjunctions in there as well. So it's not just a big and of a bunch of inequalities, it's a big and of a bunch of ors. And that problem, you don't approach in the same way as you'd approach an integer program. You instead approach it like a satisfiability problem. You basically do a sort of backtracking search, right? Looking at different branches of the different ways the ors could go. And when you run into an unsatisfiable branch, you can do what's called clause learning, which is you can look at the sort of core that made those things unsatisfiable and derive a new constraint that you add to your set of working constraints. This approach makes solving these quite a bit more feasible than solving large integer programs.
Oh, so does it mean you haven't made use of commercial solvers like Garobi?
No, I don't use Garobi. I mean, the software that I use is listed on this final table here. They're what people call SMT solvers or automated theorem provers. So I've tried Z3 from Microsoft here. I've tried CBC5 just from over there in the computer science department. Clark Barrett over in CS works on this. And then MathSat is, I believe, authored by a European team somewhere. And then Bitwutzla is a new experimental one of these that's especially good at doing bit manipulations, they would suggest. But yeah, these are all, sort of free open source. I'm not aware actually of any commercial software that does this precise task of SMT solving. I think that there's a lot of commercial interest that's been put into CBC5. So I know that Clark Barrett does a lot of work with Amazon in particular. They use this for verifying their distributed and concurrent protocols. They use this to solve these satisfiability problems looking for deadlocks in their system. It's a quite interesting application. But no, so no Garobi is present here, or indeed any software that I paid for.
It's just that Garobi makes most of its money solving integer or mixed integer problems.
Indeed.
But you've found a quicker way than that.
Yes, no, it would seem.
Oh, well, we better wrap up by thanking the Zoom audience. I'm glad David managed to make it work. Thanks for being there. And thanks everyone, every real person here. David, thank you.
Thank you very much.
Done. Good luck with finishing up.
Much appreciated.
The most important part about a thesis is the completion.
Yeah, that's the hardest part for sure. All right. Goodbye to everybody in Zoom land. Thank you very much for attending.